what I want to talk about today is joint work with Sara Veneziale and Kasprzyk. And what I want to illustrate by means of an example is what I think is a really powerful and new approach to doing mathematics. So using artificial intelligence and machine learning tools to guide human discovery, human understanding in maths. Essentially using AI as a tool to guide mathematical research. So let me say, sort of in broadest overview, what I'm what am I talking about? So I'm talking about a pipeline where you start by formulating a mathematical question. So in our case, this is going to be, how can we tell if an algebraic variety has what are called terminal singularities? Oh, I was being completely serious about the questions thing. So because this is, I mean, one of the joys of interdisciplinary conferences is that you can actually come out of them knowing strictly more than when you walked into them. And so if I'm being, I'm going to come back and sort of say more about what the objects are, what terminal singularities are, why we make care, and so on. But if I'm being unclear or you're just slightly confused at any point, please do ask. Okay, so we start off with formulating a mathematical question, and then collect some data on this question, and then use tools from machine learning to build a machine learning model, machine learning classifier that answers or tries to answer your question. To build a model. And here, at the moment, I'm really talking about using what in other parts of science are really kind of the sort of standard machine learning toolbox. So sort of linear models or sort of neural networks, the sort of, it seems that at the moment at least, because this approach to pure mathematics is new, that one can make a lot of progress just using things without inventing new machine learning necessarily. So kind of using tools that are already out there. And then let's suppose that you're in a situation where you've done this, and then suppose that your classifier suppose that your classifier really does appear to solve the problem with high probability. So suppose that you've built what appears to be an effective model for answering your question on your data set. Then, you know, there are two different directions you can take this, and you can use, and I'm going to talk about this in our example, you can use the existence of the classifier as a hint that the problem is solvable, as a guide towards what theorems you might want to formulate. And in an ideal world, you would also use information from the model itself to guide you in stating and proving your theorem. So in our setting, what we're going to come out with is we're going to come out with a new criterion for having terminal singularities, which applies to a certain class of toric varieties, was not previously known. And there's also another thing that you could do from here. So suppose you've got a model that appears to solve your mathematical question. My mathematical question has disappeared off the top of my screen, but imagine it's here. So you can use the classifier itself to kind of drive or build mathematical understanding beyond the reach, beyond our current theoretical reach. So, beyond what we can prove. So in our case, what we're going to see is we're going to use the classifier that we build to give the first sketch of the landscape of higher dimensional Fano varieties. I'm really sorry. I'm going to go back and remember to put the word Fano in here. I'm going to say what this means in a minute. It's a positively curved algebraic variety. So our question is going to be about detecting how bad singularities of what are called Fano varieties are. And the output is going to be this the output is going to be firstly a new theorem, and secondly, a new, the first sketch of the landscape of higher dimensional Q-Fano varieties. So Fano varieties in dimension 8. So I'm going to come back and say more about all of this, but this is kind of the sort of first breakthrough work here is along similar lines. Davies et al. So this is a paper called Advancing Mathematics by Guiding Human Intuition using AI. So this is in Nature in 2021, and it proposes a similar pipeline for certain questions in knot theory and in representation theory. So it's very inspirational work. So in this sense, the contribution of what I want to talk about is partly to demonstrate that, so this part of the pipeline on the left is applicable maybe quite broadly within pure mathematics, and also to point out that we can use, this idea that you can use machine learning models to explore mathematical data sets beyond the reach of current sort of theoretical understanding. This is very close to the ideas in machine learning around the use of synthetic data and so forth. So I guess the other point I want to draw out is that this is potentially also has applicability within pure mathematics. Right, okay, so far, let me just check the Zoom room. Can you make enthusiastic thumbs up noises or potentially drop questions into the chat?
Yeah, there's no questions.
Super. Okay. So, right. So the plan. Very sorry. Say again. Thank you. Yeah. I see. Super. Please increase the font. I will try my very best. Okay. So. Okay, plan for the rest of the talk. So I want to start with some subliminal messaging. I want to talk a little bit about the context for this work. So why do we care about this question? why are terminal singularities interesting? Why are Fano varieties important? To sort of set out the context for the work. I want to think about, I want to explain a little about toric varieties, what they are and how to construct them. We're particularly going to think about toric varieties of Picard rank 2. We'll say a little bit more about. Then I want to formulate our question precisely. And then I want to talk about the process of building a classifier and the results that we find. And as I said, so the results are a new and sort of rigorously proved combinatorial criterion for a Fano toric variety of Picard rank 2 to have terminal singularities. So a new theorem, and then a sketch of the landscape, an approximate sketch of the landscape of 8-dimensional what are called Q-Fano varieties, which I'm going to define in a minute. Okay, so right, so what about subliminal messaging? So ideally, I'd like you to take kind of 2 things away from this talk at the end. So the firstly, the kind of the shape of the pipeline, the methodology, and the fact that this is potentially very broadly applicable within pure mathematics. Sort of maybe, hopefully might spark curiosity about how you could potentially use this sort of thing in your own work. And also, Sarah, my PhD student, joined supervisor, Al is on the job market at the end of the year. So, I mean, this is part of a really remarkable body of work, kind of pioneering the application of machine learning methods to generating new rigorous insight into pure maths. So if you could just file that in the back of your mind, that'd be super. Okay, so we're going to be talking about algebraic varieties, which are the geometric shapes defined by systems of polynomial equations. Sorry. So what we'd like to understand these, we'd like to classify them as much as possible. In our case, we're going to be working with algebraic varieties over the complex numbers. That's not going to be super important in what follows. And the first thing to say is that, you know, depending on the equations, algebraic varieties can be smooth or they can be singular. So just as an example, you know, if I think about the subvariety of 3-dimensional space with coordinates x, y, and z, defined by the equation x squared plus y squared is z plus 1, looks a bit like this. Kind of hyperboloid of one sheet. So that is a smooth algebraic variety. And you know, if we were thinking instead about x squared plus y squared equals z squared, well, if you're thinking about x squared plus y squared is z squared plus 1, it looks like this. Can you imagine turning that 1 down slowly? So turn it down to a half, and this neck will get narrower. And as you turn it down to 0, the neck goes away completely, and the algebraic variety becomes singular. So depending on the equations, algebraic varieties can be smooth or singular. At this point, it would be quite reasonable to be grumpy and say, Tom, you told me a minute ago we were considering algebraic varieties over C, and now you are drawing pictures that are obviously real surfaces, and you're completely right. And it's just I can't draw it in complex 2 space, right? Complex 3 space. So these are pictures of the real locus within the complex algebraic variety. Can I just put something on the table for later? In a minute, we're going to be talking about toric varieties. And toric varieties are very symmetrical algebraic varieties. And an n-dimensional toric variety has an n-dimensional torus worth of symmetries. And in fact, both of these are 2-dimensional toric varieties. So they should have a 2-dimensional torus, S1 cross S1, worth of symmetries. I claim that we can see one of those S1s. And we rather embarrassingly can't see the other S1. And that's because of how I've drawn it. Essentially, it's because it doesn't preserve the real locus. So you can't see it in the picture that I've drawn. So, but later on, these are both going to be examples of 2-dimensional toric varieties, and that's why they look rather symmetrical. Okay. Okay, so far? Okay, so, right, there was this idea that we were going to start with algebraic varieties. So we were going to start with geometric objects defined by systems of polynomial equations, and we were going to try to classify them, try to understand and classify them. So let me say a little bit of what I mean by classify. One possible classification question you could ask, and this is related to what's called the minimal model program. One of the really great achievements in geometry over the last 50 years, and a lot of progress in the last sort of 10 to 15. Okay, so the general idea is that you're classifying algebraic varieties up to what are called birational transformations. I do wish that would stop happening. And so you should think of these as kind of like small modifications. So you are allowed to change the equations that define your algebraic variety, but you're only allowed to do it in a way that changes your geometry on a 0 volume subset, on a subset of codimension at least 1. So in other words, the dimension of the things that change has to be strictly less than the dimension of the thing you're thinking about. Okay, so this is not essential. One sec. So if you're a topologist, then you might be familiar with the idea of surgery operations, where you take your topological space and you do some kind of like twist on it on some small subset. These are the algebraic geometry analog of surgeries. Question. Algebraic varieties up to birational transformation. No, indeed, absolutely. So, and what does it say? So what it says is that up to birational transformations, any algebraic variety can be decomposed into basic pieces of 3 types. Positively curved pieces, which are called Fano varieties, flat pieces, which are called Calabi-Yau varieties, and many people in the room get quite excited about these, and negatively curved pieces, which are called general type, algebraic varieties of general type. So, what I've written on the board is good as a kind of intuitive overview. Can I say a slightly more precise thing? So the statement is, after birational transformations, I can make any algebraic variety into a Calabi-Yau fibration over a Calabi-Yau fibration over a Calabi-Yau fibration over a something which is either a Fano or a general type. So what I mean by fibration is, sorry, okay, I'm not going to explain that. If you know what fibration is, that's great. But the general idea is that the operation of decomposing into basic pieces is weaving from simpler pieces, right? You're weaving these things as fibers of fiber bundles. Okay. Right, so can I say slightly more precisely what I mean by positively curved, flat, and negatively curved? Okay, so you hand me an algebraic variety, X. Let's assume that it's projective. In other words, it's sitting inside projective space. And it's going to satisfy a condition on only having mild singularity, on only having like non-disgusting singularities called being normal. Now, if you know what a normal variety is, then hold that in your mind. But I'm going to talk about smooth varieties, which are normal. And what I'm going to say will remain true for normal varieties. And if you know what normal varieties are, then you can follow along with normal varieties and you can feel like pleased and comfortable. Okay, so you give me an algebraic variety and I take the cotangent bundle of my variety. I'm allowed to do that because it's smooth, right? And I'm going to take the top exterior power of the cotangent bundle. That is a line bundle whose sections are holomorphic differential forms, right? So that line bundle, okay, if you're thinking about normal varieties, it's only a, whatever it's called, reflexive sheaf or something, but that's okay because you are on top of this. These things have first Chern classes. So you take the first, that thing has a name. This thing is called the canonical bundle. And you take the first Chern class of the dual of the canonical bundle. So that's a two form, right? So, it's a two-dimensional cohomology class. And then there are three possibilities. Or sorry, the three things that I wrote here, positively curved, flat, negatively curved, mean the first Chern class is positive in the Fano case, 0 in the Calabi-Yau case, and negative in the general type case. So at this point, you might be irked or upset because things being positive, 0, or negative normally means they're numbers, right? And this is a cohomology class. What does it mean for a cohomology class to be positive, 0, or negative? Okay. Well, the thing is, this first Chern class is living in H upper 2 of X. So this is where this person lives in here, right? And can I just think about H lower 2 of X, the dual So let's think about the second homology group. That's the dual. This is where classes of curves live, right? Because curves are real two-dimensional objects. They're complex one-dimensional objects. Right, so inside H lower 2 here is the cone generated by algebraic curves. That's really a proper cone because you know that holomorphic curves have positive symplectic area. I don't know if you know that. That's a fundamental thing about symplectic geometry. Symplectic area. So if you choose a symplectic form compatible with your complex structure, then a holomorphic curve has a positive area. That's quite helpful because your symplectic structure is a two form, and it divides this space into two halves, the bit where I'm positive and the bit where I'm negative. And that means that all the curves are in one of these halves. Yeah, and you know that being symplectic is an open condition. So if you could just wiggle your curve a bit, you've discovered that your cone is actually really genuinely a cone. Like, okay, so you've got this cone inside here, and positive mean, and we're going to say that a two form is positive if it's positive on that cone. So it makes sense so these statements now make sense. And Fano is like a positive curvature condition. Calabi-Yau is a flatness condition. That's what Yau's proof of Calabi conjecture tells us. Says that there's a Ricci flat metric on the space if it's if the first term passes 0, and general type is a negative curvature condition. Question? So I cheated because at the very, very beginning I said I am projective. So I've definitely got O1 from the projective space on. So yes, I am Kähler. So right. So, and in fact, I'm stuck in the Kähler world for my entire talk. So thanks. Okay, so can we just say, what are we doing, right? We were going to take algebraic varieties and we're going to run the minimal model program. We're going to decompose them into basic pieces. It's like kind of decomposing your shape into building blocks. And there are basic pieces of 3 different types. There's Fano varieties, Calabi-Yau varieties, general type varieties. So what we'd like to understand is we'd like to understand Fano varieties. Well, actually, we'd like to understand all of them. But the Fano classification problem is going to be much easier than either of the other two. Because, for example, we know that there are finitely many smooth Fano varieties in any dimension. So it at least makes sense to ask the question, can I enumerate them? We don't know whether there are even finitely many topological types of Calabi-Yaus, even though in practice, I think one of the most effective ways of constructing Calabi-Yaus is starting with a Fano variety and taking an anti-canonical section. So even if you only care about Calabi-Yaus, you should be quite keen on this just as a way of making just as a way of making Calabi-Yau varieties. Okay, so do you remember we made these small modifications? Actually, sorry, wait, I need to say one more thing first. So, so a question we might be interested in, for example, is we might be interested in understanding smooth Fano varieties. There are finitely many in each dimension. Oh, by the way, there's one in dimension 1. If we think about one-dimensional algebraic varieties, those are curves, right? So they are the Riemann sphere or the torus or a genus 2 Riemann surface or a genus 3 Riemann surface and so on. And the Riemann sphere is Fano, the elliptic curve is Calabi-Yau, and everything else is general type. So, okay, there's one Fano variety which is smooth in dimension 1. There are 10 smooth Fano varieties in dimension 2. These are the Del Pezzo surfaces. And there are 105 smooth Fano varieties in dimension 3. That follows from this quite beautiful work by Mori and Mukai in the late 80s and early 90s. It's applying Mori's theory of minimal models and to work out that there are, in fact, only 105 smooth Fano threefolds. If you want to know beyond dimension 3, we just don't have any idea. There is a theoretical bound in dimension, well, in every dimension, right? But in dimension 4, the theoretical bound is like 10 squillion. You can just keep writing. It's not very effective. So you can just basically keep writing zeros, and that's the bound. And then we actually know about 700, maybe 1,000 examples. So there's a very big gap between theory and understanding. Anyway, so we'd like to understand and classify Fano varieties, but there was kind of a point, which was, do you remember we were making small modifications, these birational transformations? Those don't preserve smoothness. Because, for example, so an example of one of these transformations would be blowing up a point. So if you do the reverse of that, it's blowing down some stuff, and that can create singularities. So you've got blow ups, blow downs, flips, flops. So they don't preserve smoothness. So this, from that perspective, classifying smooth Fano varieties is the wrong question, right? However, there is a slightly weaker condition called being Q-Fano, or having, so this is not preserved by the transformations that you need to run in the minimal model program, but there's a kind of, so there's a sort of smooth algebraic varieties live here, and then there's a sort of slightly bigger set called algebraic varieties with Q factorial terminal singularities. So these are kind of mild singularities, contain smooth, slightly bigger, closed under the minimal model program. So what we'd like to do is we'd like to understand and classify Fano varieties with Q factorial terminal singularities. So let's make a definition. X is a Q Fano variety if and only if X is a projective variety with these mild singularities that I'm not going to define in general, but I'm going to define in the case that we use. So but you can think of this as a mild class of singularities that's kind of natural from the point of view of binational geometry, and the first chain class of minus kx is positive. Okay, so this is our question now. Can we give an effective criterion, an efficient way for a Fano variety to have terminal singularities? You might say, why have I not got Q factorial in the question as well? It just turns out that Q factorial in the context, checking Q factoriality in the context that we're about to be in is easy. So this is the interesting bit, or the hard bit. Okay, so far. Okay, on Zoom. I'm going to assume yes. Sorry, let's try and get the font bigger again. Okay, so what we're going to do is we're going to investigate this question for toric varieties. And so, as we said, these are highly symmetrical algebraic varieties that have a dense torus inside them and carry the action of a large torus. An n-dimensional toric variety has an n-dimensional torus worth of symmetries. So the example that you're all familiar with is going to be n-dimensional projective space, where you take c to the n plus 1 and you remove the origin and you divide by the action of c star. You decide that lambda acts on the vector x0 through xn by scaling the coefficients, and you take the quotient by the equivalence relation given by this action. Put differently, you're looking at the lines through the origin, right? That's what these orbits are. So that's kind of a more classical description of projective space. So exercise. This is a toric variety. So, you know, you might decide to write the equivalence class of x0 to xn like this, and then I'm supposed to find an action of an n-dimensional torus on this person. I'm going to leave that for you guys, but there is an action of the n-dimensional torus, and inside this person is an n-dimensional torus, because if I look at these people, where the last coordinate is 1, that's actually, if I just insist that none of these numbers are 0, then I found myself a c star to the n inside this person. You need to check that there's the action as well, but there is. Okay, so we're going to, so you might be familiar with toric. If you've seen toric varieties before, they might have been constructed for you in terms of something called a fan, which is where you have a bunch of cones in some vector space, and that gives you charts on your toric variety, and you glue together the charts in a way that's given by the gluing together of the cones. So for projective space, this kind of presentation as a quotient is probably simpler to understand. If you've seen the fan picture, then I don't know whether the fan for projective space is the first thing you would think of. Maybe, I don't know. But anyway, this kind of quotient perspective is quite a useful one, and we're going to use it again in the examples that we consider for our question. So we're going to consider a generalization of this. So to toric varieties of what are called Picard rank 2. So if you give me an integer matrix satisfying some conditions, so no 0 columns, and the columns span a strictly convex cone in R2, then I'm going to make for you a variety. So I'm going to decide that C star, I'm going to use this matrix to define an action of C star squared on C to the n. I'm going to decide that lambda and mu in C star squared acts on x1 through xn as lambda to the a1 mu to the b1 x1 blah 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 lambda to the an mu to the bn xn. So do you see that I've got c to the n, and now I've got this action of c star squared. So most of the orbits are going to be two-dimensional because most of the orbits are going to be copies of c star squared. The origin is kind of weird because it just stays where it is. It's just a zero-dimensional orbit. But I'm also going to need to delete some other bad orbits. I'm going to decide that if I set A to be the sum of the AIs and B to be the sum of the BIs, then I can define two subspaces, which I'm going to delete. So I'm going to define two linear subspaces. And then I'm going to take X to be C to the N minus the union of these linear subspaces divided by C star squared. Tell me again. What's the ambient? Oh, so yeah. So I'm just summing the. So for projective space, I took C to the N. I removed the origin, which was a linear subspace, and then I divided by C star. Here, I take C to the N. I remove some linear subspaces, and I divide by C star squared. And if I also insist that, so most of the time, the dimension of S plus and the dimension of S minus are both at least 2. So I'm going to assume that in what follows, and that implies that the second Betti number of this space is 2. So it's the dimension of H of the second homology group is 2. So this space has Picard rank 2. So these are toric varieties of Picard rank 2. So question, can we tell from the weight data, from the weight matrix, if X has terminal singularities? So, can we just think about the weight matrix for a minute? Can we just think about this person up here? Can you see how, if I permute the columns, it doesn't actually change the quotient that I get. I get an isomorphic quotient variety. It's just that instead of writing vectors like this, I've shuffled the order of my entries in my vector, but it doesn't actually matter. I still get an isomorphic quotient. And similarly, so column permutations don't matter. Similarly, row operations don't matter. That's slightly less obvious. It involves reparameterizing the torus rather than reparameterizing the space. But column permutations don't matter. Row operations don't matter. They give me the same quotient. So I could potentially put my matrix in normal form with respect to, oh, sorry, I guess if I'm, so what I'm saying is that SL2Z cross SN acts. I might mean GL2Z. I probably mean GL2Z. Right, because row operations, I'm allowed to swap rows, right? So yes, okay, GL2Z cross SN acts on the space of weight matrices, and that doesn't change the algebraic variety that I get. So I'm not so much interested in weight matrices, I'm interested in weight matrices up to this action. And if I put an extra technical condition on my weight matrices, which I'm not going to tell you about, which is called being well formed, then one of these varieties, Picard, then a toric variety, determines and is determined by its weight matrix up to this action. So why am I telling you this? In a minute, we're about to build a machine learning model to answer a question about geometry, right? So, and you need to feed your machine learning model a vector of features, right? You need to take your geometry and you need to turn it into a vector of numbers. That's generally brutally hard to do in a, that generally requires serious thought to do in a meaningful way, right? Because you'll have, how is your variety presented? Maybe it's presented in terms of some equations. Then you have to start thinking about how to turn those equations into a feature vector in a meaningful way. Notice that we are in a wonderful situation where the construction of our algebraic variety involves a vector. Okay, fine. It's actually a matrix. If you don't mind putting the second row after the first row, then it turns into a vector, right? So this problem is really nicely vectorized for machine learning methods. Okay, so what are we going to do? We're going to take weight matrices in normal form with respect to this action. And we're going to say, if I give you one of these people, sorry, let me just tell you what the normal form is. So here, the columns are cyclically ordered anti-clockwise. All entries are positive. Maybe I mean non-negative, actually, sorry, non-negative. And AN is less than BN. So you can always using the action, you can always put weight matrix of rank 2 into that form. Okay, so if you give me this person, can I tell you whether the corresponding algebraic variety has terminal singularities or not? Telling whether something has terminal singularities is a hard problem. So prior to this work, how you would have to approach this is you would take the toric variety, find what the corresponding fan, which I haven't told you about, it's a different way of presenting the toric variety. And then for each cone in the fan, there's a hyperplane which contains the first entry, the first integer point along each ray. So you take the generators, you take the first integer point along each ray, you put the hyperplane there. The toric varieties have to be Q factorial, which means the cones are simplicial. So there is a hyperplane. So if you're worried about why all these things need to line up on a hyperplane, it's because the cones actually have the right number of points in them to determine the hyperplane. Okay, so you find all these hyperplanes and you have to check whether there's any integer point in this cone strictly below that hyperplane, except other than the origin. And that's a perfectly reasonable integer linear programming problem. It's just that there's not any effective way of solving it. You know, you just have to do the integer linear programming problem. What you'd actually like is you'd like some kind of effective criterion that analyzed the weights and said, for this lot of weights, they're terminal. For this lot of weights, they're not terminal. And that is not, well, was not known. Question? But no, because so no, and the reason that is hidden in the thing where I said, and some technical condition that I did not tell you. So, firstly, if I'm just multiplying the row by 2, right, that's 2, 0, 0, 1 acting on the left. So that's not GL2, right? It's in GL2Q, but it's not in GL2Z. Yeah, so why is it different? Well, what's going to happen is there's going to be a Z mod 2Z symmetry group along one entire divisor in your toric variety. And the condition that I'm ruling out, called well-formedness, means that I want my, the condition that I'm not mentioning, called well-formedness, makes sure that I don't have singularities in codimension 1. I only have them in codimension 2. So that's exactly the issue. Cool. Okay, so question, can we work out in terms of the weights whether or not this thing has Q-factorial terminal singularities? In any given example, we can by doing the integer linear programming calculation. It's just really quite hard. However, this is in kind of an ideal format to feed to a machine learning question. So a machine learning classifier. So what we did is we randomly generated weight matrices in normal form, where the weights were bounded by 7. So we sort of weight matrices that fit in a 7 by 7 box. Well, 7 by 7 by 7 by 7 by box. And we generated 10 million examples, half of which are terminal, half of which are not terminal. To give you a sense of the difficulty of the terminality checking, that took 30 CPU years. Right, so that's quite a lot of computation. That's like you shouldn't run this on your desktop. This is a cluster scale computation. So so we take our 10 million strong balanced data set and trained a neural network classifier on it. So we train a multi-layer perceptron with 3 hidden layers. In fact, sorry, if I just switch for a minute. Yeah, so these are the network parameters. So not super deep, not super big, but like a simple neural network of moderate size. And we train it on the classification question, do these weights give a terminal toric variety? And training for not a long time, training for about 4 hours, 150 epochs of this data on training on half of the data and testing on the remaining half, end up with 95% accuracy for this question. So that's a pretty substantial clue that there's a mathematical result here, right? And so at this point, I guess, if we just go back to the, if we go back to the paradigm at the beginning, the fact that the classifier exists suggests that there's a theorem. So we should go find that theorem. That's actually quite useful because a lot of the time you don't know whether there is a theorem or not, right? That's like believing is quite helpful, especially because, sorry, if you're, this is not something I myself understand very well, but if you are a specialist in the theory of polytopes, there are sophisticated reasons that suggest to you that this problem might be hard. So this is an unsophisticated reason that suggests that maybe you should keep going. And so, okay, so we end up stating and proving a new effective combinatorial criterion to detect Q-Fano varieties. And it's a lot more effective than the integer linear programming method. It's maybe 15 times faster. What's kind of interesting is it's between 20 and 2,000 times slower than the neural network. So there is some possibility that maybe this is actually not the best. Maybe this is not the final form of the result. You know, here is a new result, but the classifier is still outperforming the new rigorous result by a lot. On the other hand, do you remember our data set was randomly generated on this box of size 7. So you could ask yourself, okay, so what happens if I use some, if I evaluate this in out of sample data, if I try it on like data where weight matrices where though I'm allowed numbers up to 8 or up to 9, and it does really quite badly for 8 and no better than chance for 9. So the classifier that we have does not work very well out of sample. So if you are an optimistic person, you say, look, this is fine. There's still some better results out there. It's just that machine learning models often don't work out well out of sample, which is true, right? But there's also the possibility that maybe what's happening is our data set, because we bounded our weights, that bounds how bad the singularities of this variety can be. It bounds something called the index of the singularity. So maybe there's only some fast method for singularities of low index, and we were just very, very lucky and happened to choose a box that fitted inside the low index. Okay, so it's unclear. In any case, so the first output is new theorem. The second output, I'm very sorry, I'm going to overrun by about 3 minutes because I really like this bit and I want to tell you it. Okay, so what you might want to do you remember you were kind of, so we were trying to understand the sort of landscape of Q-Fano varieties, right? And now we have this machine learning classifier, which tells us with high probability whether a Q-Fano variety whether a toric variety of Picard rank 2 is Q-Fano or not. So rather than doing this excruciating data generation process, which takes literally CPU years, what we could do is we could use our very cheap classifier, randomly generate a bunch of data, and produce algebraic varieties that are with high probability Q-Fano. So let me show you the distribution of, Fano varieties, Q-Fano varieties of dimension 8. Sorry, just some, I need to tell you a thing. So to make sense of this, from an algebraic variety X, we can create, I need to visualize the landscape using some kind of measure. I need to get a data point corresponding to each Fano variety. I need to plot it on a graph for you, right? So I need to tell you what the axes are, right? I'm about to give you a sketch of the landscape of Fano variety, so I need to tell you what I am sketching. Okay, so if you start with a Fano variety, you can make what's called the quantum period of the Fano variety, a regularized quantum period, which is a sequence of numbers. So this is basically a number or virtual number of degree D curves in X. For people who are familiar with topologically twisted string theory, so with nonlinear sigma models in string theory, these are Gromov-Witten invariants. So you can think of these as correlators in the topologically twisted A model where your space-time is X. And so this is basically the log free energy of the topologically twisted type 2A string theory with space-time X. Anyway, so, but the point is, out of X, you can get a bunch of numbers, right? These invariants, and these are what I'm going to use to visualize the landscape. And so we proved in our paper, Machine Learning the Dimension of the Fano Variety, just about to come out in Nature Communications, that if you take the non-zero ones of these, the non-zero CD, then these grow exponentially, but they grow like AD, log of CD grows like AD minus half the dimension of x times log d plus b. So you can just look, so you can imagine taking a Fano variety and looking at the two numbers that control the rate of growth of the Genus-zero Gromf-point invariance of x. So it's a way of taking this kind of seemingly infinite amount of data that tells you what your Fano variety is and projecting it down to the plane. It's like, how fast is it growing? Take the log, find out what those coefficients are. So in our earlier work, this is what weighted projective spaces, the simplest Q-Fano varieties, look like. These are the A's and B's for various dimensions. But now what we can do is we can use this in Picard rank 2. So we generate 100 million examples of toric varieties that are with high probability Q-Fano. And we take their A's and their B's, so we make the same hedgehog plot as before, and they look like this. So it looks like, so you can see the sort of, they appear to be falling into some bounded region. And so this is for 8-dimensional Fano varieties. This is completely beyond theoretical reach. We have no idea. We can't even do this very well in dimension 3, right? So, and it seems that sort of the distance up that axis is something to do with an invariant called the Fano index, which is, do you remember we had that cohomology class earlier? That's an integer cohomology class, and you can imagine the highest common factor, the divisibility of that. Like if it's twice something, the Fano index would be 2. If it's 17 times something, Fano index would be 17. Fano index seems to go this way. And so you kind of think, okay, well, maybe smooth Fano varieties are somewhere special on this plot, right? No, it turns out. In a kind of, anyway, so this is where the smooth varieties are. This is where products of weighted projective spaces are. We do kind of understand why that right hand, that the 2.3 is log 10, which 10 is 8 plus 2, sorry. You remember we're in 8 dimensions. So add 2 and take log, and that's the right-hand boundary. But anyway, there's much to be potentially learned here, and we can't even see this landscape without the classifier. It's hopeless. So that's the end of the story. Thanks.